So hello everyone. I am Mahmoud, professor in ULB in this campus, and we are doing MobilityDB. It's a moving object database system. So it is meant for trajectory data management. Already in the talk of Vizarion, we got an idea what's a trajectory. In MobilityDB, the time dimension is also taken into account. So if you have a GPS track from your mobile or some GPS tracker, a navigation device or so on, it gives you more or less data like this. So you get some identifier for the trip, and then a sequence of point and time. Yeah, you can put this in PostGIS, in MySQL. You can use a Boost library in order to start doing data management of this. What MobilityDB does is it puts the whole trip together. So it encapsulates, it creates this structure for a trip where you have a point at timestamp and then a second point at timestamp. So you put the whole sequence together in one data type, and that becomes a data element in your table. And then you can start writing functions over it in SQL to calculate the speed, to calculate the heading, to do selections, to do joins, and so on. So generally speaking, this is a general architecture. You have PostgreSQL providing these relational types, some advanced types like XML and JSON as well. And then on top you have PostGIS, which provides two main abstractions, geometry and geography. So you can be doing maps. And then you have MobilityDB on top that provides the temporal information, that adds the temporal information to PostGIS and PostgreSQL types. So you get a temporal geometry point representing a car, for example, or a person moving over time. You get temporal geography point according to the coordinates, are they geographic or geometric. But also you get temporal float, temporal integer, temporal text, temporal boolean, and these are important for evaluating functions and predicates over trajectories. For example, the speed of a trajectory is changing over time, so that's a temporal float. You want to check a predicate of a trajectory. Is the car now inside Brussels? So the result will be a temporal boolean, because sometimes it's true, sometimes it's false. So these types have to also be supported. And you can imagine that the list of types, of temporal types, can be extended to support different applications. Right now, these are the main ones supported in MobilityDB. So MobilityDB is a vertical extension that extends PostgreSQL at all data management levels. So it extends the data model with both time types and temporal types that I just mentioned. So you can use them as attribute types in your table. It extends the indexes so that one can process fairly large tables quickly. So it extends the gist index of PostgreSQL, which is a kind of, which is R3 actually. The SPGIS, that's a space partitioning, so it's a kind of grid structure. The B3 index. It also extends a query optimizer so that one can do vacuum analyze to collect statistics about these temporal types and to be able, so that the optimizer can estimate selectivity of predicates and do its optimization stuff, invoke the indexes when relevant, try to find the best execution plan. And then a big set of operations. For example, you can always project, remove the time dimension, project to a line string, and then do all kinds of processing on a line string. If you want to include the time, Then you use the lifted operations. We call them lifted because they lift the static operations with time. So you can do arithmetic on temporal numbers, can do binary operations on temporal booleans, can do distance and topology operations on temporal points, and so on. This is all built as an extension, not a fork, to PostgreSQL. And because it's an extension, it's by default should be, we hope, compatible with other PostgreSQL, other tools in the ecosystem of PostgreSQL. We have tested with some, and we wish to test with more. For example, integrating with PG routing for calculating shortest distance, so that to support network points. You can represent the coordinates either absolute as latitude and longitude, or as map matched, like an identifier to a certain road in a road network, and the fraction of distance that is traveled to get more context. PipelineDB provides some stream processing of our PostgreSQL. We did some, let's say, toy experiment on it. We do support good integration with Citus. Citus is for scalability, so that you can run a PostgreSQL database on a cluster, and your queries get distributed. So combining both MobilityDB and Citus, one can do query big data sizes. So my colleague there is responsible for this part. For a quick start using MobilityDB, there is a Docker image, and so on. So how does it look like loading the data? The most common format is comma separated. You can always transfer whatever tracking format to some comma separated. Most important, create extension MobilityDB Cascade. That's how to start supporting these spatiotemporal operations in your PostgreSQL database. Cascade will also create extension PostGIS if it is not there. Because basically MobilityDB does manage the temporal part and its relation to spatial part, and whenever it is about spatial processing, it delegates to PostGIS. So in this table at the left, that's a pretty standard one that you would use for any for just loading the flat information you get from the GPS device. So you have longitude, latitude, and time. These are the key things, and also some identifier for the moving object and the trip. And that's the one you can use using you can do with MobilityDB. Here you see one column called the trip, which is a T geometry point. This is the one that's going to carry the complete trip. So every row in this table will represent a trip. And in order to load this table in this table and create your trips, basically you combine every point with its timestamp, do whatever projection you want in order to put it in the coordinate system required, create an instance of these, and then aggregate all instances that are for the same trip and same car, aggregate them in an array, and then put this array in a temporal geometry point. So now you have this complete trip in a single data item. To support, well, you can also use other formats, GTFS for public transport schedules, and there is a tutorial about this on the GitHub of MobilityDB that shows step by step how to create trajectories from GTFS. Google location data, if you can download your own track and then start playing with it. Actually, Google stores a lot, so it will be fun. You can start calculating aggregates, how much time you spent in driving or you spent walking, where you go. If you manage to get location data of someone else, that's becoming more interesting. And that's also another workshop, so you get a step-by-step tutorial. A third workshop that's nice is managing AIS data. This is ship data, basically. Here we use some data published from the Danish Maritime Authority. They have huge data size, like 3 terabytes of ship tracking data. This only shows a single day after some filtering. It has, so the original file is 10 million rows and 1 gigabyte, not very big, but you can go bigger. This is an application done by colleagues in Moscow who use MobilityDB to play with the public transport, well, not to play, you want to put it, with the public transport network in Moscow, and they did these nice velocity maps basically by aggregating the spatiotemporal trajectories. Yeah, very nice visualization, if it works. So this is normally, yeah, it will start moving. So that's only yesterday. Had very nice meeting with our colleague Yang Suk from the Artificial Intelligence Research Center in Japan. Actually visualizing MFJSON. MFJSON is a new to appear OGC standard. I know from the talk of Jody that not many are fan of OGC, but it is changing. OGC now is doing pretty cool stuff, including standards for moving features. So this data basically was exported from MobilityDB as MFJSON, imported in this Cesium extension, and then visualized in the moving. This is one of the ships in the AIS example. They even did some 3D, so you can see a space-time cube. This is the same shape, but now that's a spatiotemporal movement. So let's look more about queries in MobilityDB and what kind of operations you can get there. So in this example, and in the following few ones, the same ship database will be used. Basically, we have a table ships that has an identifier for a trip, that has a trip trajectory as a geometry point, temporal geometry point. Speed over ground, this is a typical observation reported by the AIS sensors that tells you the speed of the ship. And because it changes over time, it's loaded into a temporal float. So this is coming from the source information, not calculated. Course over ground, also temporal float. And then I pre-calculate the spatial trajectory, which is a line string, project the same trip into some projected coordinate system, the ETRS, which fits the area of Denmark. Now, if we want to list all the ships that commute between these two ports, Rhodaby and Puttagarden, so you have two ports and you want to see which ships commute around. So I express this in this SQL query. Basically, the two ports are represented as two rectangles, and then we are interested in the trips that intersect the two rectangles together. So that two predicates intersects. So this predicate is a MobilityDB one. It accepts a trajectory, a temporal geometry point, and some geometry, and it returns a Boolean. Yeah, and then in order to do this efficiently, you need an R tree. So you create a gist index over the projected trip column. So some gist index will be used behind the execution of this query. And this is the result. The 2 ports are the red rectangles, and then these are all the ships traversing. Another query, find the ships that have speed over ground different from the speed calculated from trajectory. Basically, in this table, you have 2 speed components. One that is coming from the sensor, SOG, and one that you can calculate from the spatiotemporal trajectory that has been constructed. Normally, they should be the same. If they are not the same, then the sensor is providing some wrong information. So I don't know why the query should be interesting. I thought it's interesting, so I try it, get everything from the table ships, and then perform a minus between the 2 speed components. We'll convert both to kilometers per hour, and then convert a minus. And this minus is a temporal minus between 2 temporal floats. So it's going to be calculating the difference at every time instant and producing a temporal float. And the time-weighted average will summarize this temporal float into a single float and compares if the speed difference is greater than 10, then show me this trip. So this is what I just explained. You have 2 speed components. The one calculated, the blue one is the one calculated from the spatiotemporal trajectory. The orange one is the one SOG. If you do a temporal minus, this is what you get. And then you summarize this using time-weighted average to get a single float. I didn't put a result here, but we got some trips that really showed noise. This is another query for an aggregation. So here it aggregates the length of the trips in per day, per hour. So basically, we want to see what is the distance traveled per ships every hour. So every hour in the day, how many? What is the total distance traveled by all ships, as an indicator of how busy the Danish water is every hour. So we create a relation of 24 periods, the 24 hours, and for every period, we restrict the trajectory to this period, and then just calculate the length in kilometers of the trip, and do a regular sum over these, group by the period. So you get something like this. So per hour, this is the total traversed distance by all the ships. Nothing interesting. More or less, it is the same all the day, but the query is interesting. This is a temporal aggregate. So in the previous one, we did a sum. Here, that's a temporal sum. And it is using the operator cumulative length. Cumulative length at every time instant, it tells what is the distance that has been traversed so far from the beginning of the trip. So the result is a temporal float. And now you have multiple temporal floats per trip. So you do a temporal sum, which will sum these temporal floats at every time instant. And the result is a temporal float that looks like this. So this is a time, this is a distance. And you see that it is steep increasing, which confirms the previous query that there's no difference according to the hour or the time. This is another trip to do a join. Here we want to see whether there were some danger situations in the data set where 2 ships came very close to one another. And for this predicate distance within, taking 2 trajectories and checking whether they have ever came to 300 meters close to one another. So this query is self-joining the ship to itself. And if so, for these trajectories, show me the shortest line between the 2 trajectories. So the result is something like this. The blue ships and the green ships, whenever a blue ship comes close to a green ship, 300 meters or less, we see this red line. So the ones above are at the entrance of the port. So that's not a big deal. Ships are going slow, they are entering the port. But maybe this one is more interesting because it happens just in the middle. Two ships are coming close to one another. Maybe one would like to further look at their direction, their speed, where they're heading towards one another. So you can continue writing, adding more complexity to the SQL. This is what I mentioned in the beginning. You can run this on a cluster. Just put on every node Citus, MobilityDB, PostgreSQL, and PostGIS. The data will be sharded and replicated. And then the user query, you have few management commands to shard your data and to create reference tables and so on. And then everything else is transparent. You just write the query, it gets distributed. And we saw that on 4 machines, we gain like, the queries become 20 times faster. So to end, MobilityDB is a moving object database system. It's an extension of PostgreSQL and PostGIS. It's developed by the team in ULB. It's open source, it's available on GitHub, and it's compliant with the OGC standard for moving features, the new development that is happening over there. So, yeah, it doesn't show the last slide. Thank you
very much. We have 1 minute for one question, and even a short one at that.
Please.
Could you speak up a little?
Could it be used for air traffic management? So basically, as I understand, we have 2-dimensional elements via PostGIS. Would it be, or is it already able for MobilityDB to find the distances between flying airplanes, but we need to add the height to it?
Yes and no. It builds on top of the PostGIS point, which can be 3-dimensional. But I know that the distance functions in PostGIS are not very accurate when they come to 3rd dimension. So the distance is done by PostGIS basically. MobilityDB will manage the time.
Okay. Thank you very much again.
Thank you.